Hello everyone and welcome to my channel. My name is RF and today we're going to talk about maximum power transfer to load. So this theorem is a complementary theorem of Thevenin theorem. So if you haven't seen my previous videos on Thevenin theorem, I highly recommend you go back there and try to study the Thevenin theorem first before starting this one. And as always, if you like the contents of what I've provided, please don't forget to like it and share it with your friends and subscribe to my channel. Thank you very much. So let's get started. Max power transfer to the load. So why are we interested and what actually it means? So the RL that we have at the end of the circuit is actually our load. And from previous lessons, we know that everything to the left of the load, and I say left based off this circuit, not just to the left. What I mean is if we see our circuit from our load's perspective. So if I stay here and this is my eye, and I try to watch the circuit from this perspective, what I see is an independent voltage source that we know that we call this Thevenin voltage, in series with a Thevenin resistor. So this Thevenin resistor and this Thevenin voltage is the representative of a bunch of resistors and dependent and independent voltage sources and current sources. So what are some applications of max power transfer? So why are we interested? And how it helps. There are multiple applications, so I've listed just some of them. For example, in electronic devices, so in all portable electronic devices like smartphones and laptops and tablets, the max power transfer theorem is applied to match the internal load resistance with the source resistance. In a nutshell, for a linear DC network, the max power transfer theorem states that the power delivered to a load is maximized when the Thevenin resistor and the load resistor are equal. Why? We're going to delve more into this. So just in a nutshell, remember, in order for the power to be maximized, to be delivered to our load, the condition is that our load must be equal to the Thevenin resistor seen from our load's perspective. So the mathematical proof is that if we consider this circuit here, so I'm going to just redraw it. So we have the Thevenin voltage in series with our Thevenin resistor, and here is our load. And there's a current flowing into this circuit. Let's call it IL. So this current, based off the Ohm's law, we know that current is voltage divided by resistor. So that would be Thevenin resistor divided by RL plus R Thevenin. So this is exactly written here. And then the power delivered to the load, we know there are several derivations of power, but the consumed power is I squared R. So I squared RL is the power delivered to the load. So I know that from Ohm's law, I equals V over R. And here, I is V Thevenin divided by R Thevenin plus R load. So if I want to just form I squared, that would be V Thevenin squared divided by R Thevenin plus R load squared and times RL. Okay, continue on. And we know from math that to optimize an equation with respect to a variable, we should differentiate both sides of that equation with respect to that particular variable. Our variable here is RL, which is the load resistor. Okay, so I'm trying to maximize this equation with respect to RL. So to maximize PL, which is the power transferred to the load, we differentiate with respect to RL, and then we set that derivative to 0. So I'm going to just differentiate PL with respect to RL. So if we consider this as U over V, and I'm trying to differentiate it, U over V prime gives me U prime times V minus V prime times U over V squared. That's exactly what's done here. So if I differentiate my numerator with respect to RL, that becomes this with Thevenin squared times V, which is my denominator, R Thevenin plus RL squared, minus V prime U. So that would be the derivative of my denominator, which is 2 times R Thevenin plus RL times the derivation of this term, which is just 1, okay, times U, which is with Thevenin squared times RL. So in order to zero out this equation, all I need to do is to zero out the numerator. So I don't care about the denominator. So all I need to do is to zero out the numerator. And from here, I can conclude that R Thevenin minus RL has to be 0. And that gives me the condition of the maximum power transfer to the load, which is what we have just decided. RL has to be equal to R Thevenin. So the max power transfer to the load occurs only when the load equals the Thevenin resistor. Now that we have decided the condition of max power transfer to the load, it's time to solve the max power now. If RL equals RS in this circuit, how much power is delivered to RL? So from here, and from voltage divider rules, I know that if these two resistors are equal, so they share the same amount of voltage drop across them. So the voltage drop of RS equals the voltage drop of RL. So VRL equals VRS. And they has to add up to Vs, which is the source voltage. So each one of them share Vs over 2. So Vs over 2 is the voltage across RL. So the power consumed by RL is V squared over R. That's another derivation of power formula. If we consider I squared R, and then I just substitute I with V over R, that would be V squared over R squared times R. So just this square cancels out with R, and V squared over R is another derivation of power consumed. So I just substitute Vs over 2 over here, and what I have is V squared over 2, Vs over 2 squared over R, and I come to conclusion that the max power transfer to the load is actually V squared over 4 times RL. And this V is the voltage of the source. That's Vs. I can just simply say V Thevenin. So the max power transfer to the load is nothing but V Thevenin squared over 4 times R Thevenin. R Thevenin here is the same as R load. So now let's solve a problem to make sure that we understood everything. So in this circuit, we're trying to find the max power transferred to the load, which is this RL at the middle of this circuit. And we know that the max power is nothing but V Thevenin squared over 4 times R Thevenin. So to solve the problem, we need to figure out V Thevenin and R Thevenin. And we are using the same techniques that we learned from the last sessions. If you remember, for R Thevenin, we open the circuit from load's point of view and we try to figure out the equivalent resistor seen from load's perspective. So we have our load here. So I open the circuit from my load's perspective, and then we turn off all the independent sources. So I have this 4 amp and this 60 volt. So if I want to turn off a current source, it changes to an open circuit. On the other hand, for a voltage source, it changes to a short circuit, like this, just a piece of wire. And then I have 10 ohms at the bottom, and there's this 20 ohms in parallel with this 5 ohms. So this 20 ohm and this 5 ohm are in parallel because the heads and the tails are connected to the same point. And we know from previous sessions, if the heads and tails of two resistors are connected to each other, those two resistors are in parallel. And the equivalent resistor would be this times this over this plus this. So another way is that if one of the resistors is n times bigger than the other one, the equivalent becomes the bigger one over n plus 1. Here n is 4, so 4 plus 1, which is 5. 20 over 5 becomes 4 ohms. So the equivalent resistor of 20 parallel with 5 is 4. And then I have 10 ohms here and 30 ohms here. So these three, let me just simplify the circuit more. So I have 30 ohms, 10 ohms, and the parallel of 20 and 5, which we figured out to be 4 ohms. And here is port AB, from which we are trying to see the equivalent resistor, which is our Thevenin resistor. So 30, 10, and 4 are in series. As a result, the Thevenin resistor is just the addition of these three. 30 plus 10 is 40, plus 4 is 44 ohms, is my Thevenin resistor. Now let's continue on to figure out our Thevenin voltage. So I'm going to just redraw the circuit to make it a little cleaner for our Thevenin voltage. Alright. Now let's try to figure out the Thevenin voltage. In order to calculate the Thevenin voltage, we know that we should open the circuit from load's point of view, which is from these 2 points, let's call it A and B, and then try to figure out the open circuit voltage seen from load's perspective. So if I want to simplify that circuit, it becomes a 30 ohm at the left, and then this open source, and then I have 4 amps here. There's a 10 ohm at the very bottom of the circuit. It comes to 5 ohms, and then have 60 volts, and there's a 20 ohms in parallel here, 5 and 60. Alright, let's try to figure out the Thevenin voltage now. I'm interested in knowing the voltage seen from here, port AB. So there's an open circuit here, and I'm trying to figure out the open circuit voltage at this point. So if you look closely to this circuit, it looks like the circuit has been divided into two different sections. This is the left section, and this is the right section. And there's this 10 ohm at the bottom. So I'm trying to figure out the role of this 10 ohm first. Let's see. If I consider the current which is flowing into this loop, let's call it I, and we know that the current exits the positive polarity of the voltage source and enters the negative polarity. So if this current exits the positive polarity, it reaches to this intersection, and then the circuit is open here. So there is no more current peels off here. So the whole current passes through this 20 ohms. So the current I passes through this 20 ohms and reaches to here, this intersection. And I know that this branch is the same branch of my 60 volt source. So again, the current of this branch is I. So very quickly I can figure out there is no more current peeling off here. In other words, the current of 10 ohms resistor is 0. This is a very important result because it helps me now to separate my circuit into two parts, the left part and the right part. And I know VOC is here at the middle. So if I figure out the positive polarity and the negative polarity, and each one of them, I need to figure it out separately, because the positive polarity is to be figured out from this left circuit, and the negative polarity is associated with this right circuit. Okay, so the left circuit, this one is 30 ohms here. So the positive polarity is actually the polarity across this 30 ohm resistor. So from Ohm's law, I know that this becomes 4 times 30, which is 120 volts. And the negative polarity, which is associated with this right circuit, 20 ohms, 5 ohms, and 60 volts, is nothing but the voltage across this 20 ohms. How can I figure out the voltage across this 20 ohm? First, I need to figure out the current passing through this loop. And again, from Ohm's law, I know current is voltage divided by resistor. 20 plus 5, 25. If I simplify by 5, I divide both numerator and denominator by 5, it becomes 12 over 5, or 2.4 amps. Okay, the current is 2.4 amps, and the voltage across 20 ohms is 20 times 2.4, or 2 times 24, or 48 volts. Beautiful. I have the positive polarity of VOC as 120 volt and the negative polarity of VOC as 48 volt. As a result, VOC is the positive polarity minus the negative polarity. So 120 minus 48, 72 volts. This 72 volt is my VOC, which, by the way, we know that this is our Thevenin voltage. So the Thevenin voltage is 72 volts over here. So I have the Thevenin voltage and I have the Thevenin resistor. If you remember, it was 44 ohms. From Thevenin resistor and Thevenin voltage, I know that the max power transferred to my load is V Thevenin square over 4 times R Thevenin. So let's figure it out. It's 72 square over 4 times 44. Let me quickly calculate this. 72 square over 4 times 44. 29.45. 29.45, and we know the unit of power is watt. Is watts. So 29.45 watts is the max power transferred to the load. I hope that you guys have reached the same value, and thank you very much for watching my video. If you like the contents, please don't forget to like it and share it with others. Let's help each other grow. And you're more than welcome to subscribe to my channel. Thank you very much. Have a good one. In radio and television antenna, in wireless communications, electric vehicles, and power distribution systems, the same theory applies.